Hello. Today, April 16, we are going to discuss our lecture 5 entitled Forward and Inverse Kinematics. And previously, we discussed about the Denavit-Hartenberg convention for lecture 4, where we assign frames to links of the robot, and we assign axis and all this rotation and translation around, about, and along those axes in order for us to come out with the transformation matrices from the base frame to the end effector frame. So now, today we're going to discuss how we're going to use this information of the Denavit-Hartenberg convention for forward and inverse kinematics for full space robots. So the outline of this topic is there are two. First is forward kinematics, of course, which is we come out with the result of the x, or the position and orientation, given the input of the angles of the robot. So there is this function, a forward kinematic function f, whose inputs are the joint variables q, generalized joint variables. It can be prismatic or it can be revolute, meaning the joints can be translational, like prismatic joints, where they're driven by hydraulic or air pressure. Or it could be revolute, meaning rotary joints, which can be driven by electric motors. But the output will be position and orientation, which is represented by the vector x. So that is forward kinematics. Given the joint variables, you output the end effector position and orientation, or the hand of the robot, the position and orientation of the hand of the robot. Now, let's go to inverse kinematics. For inverse kinematics, we are going to solve, or to look, or to determine, to look for or to determine what are the variables, what are the joint variables, or what are the values of the joints that will bring about the position and orientation of the hand of the robot and effector. This is the more meaningful information, because normally in the world space, we specify in our world, we specify where the hand of the robot should be in order to manipulate certain materials and to handle materials and to do certain tasks in our world. That's where the position and orientation of the workspace, or the workpiece in the workspace. And it could also be just execution of some hand processes or hand signals that doesn't, or hand motion that doesn't need to handle anything, any material. But in totality, it is the position and orientation of the hand, on how it moves in the world space that we know of. And we choose to solve using the inverse of the forward kinematic function, which is f, in this case, f inverse, to solve the inverse of that kinematic function, given the x, or the world position and orientation, as our input. And now we will be able to solve for the q, or the joint variables. So in this case, it is answering the question of what are the corresponding joint variables q that will come about to hand position and orientation, that will bring about the hand position and orientation in the world space. So just for completeness, I put this q star, which is the optimum q, optimum joint q, which will be applicable when the joint, or when the robot is redundant. So in this case here, there are many joint configurations. For example, the q variable that will bring about the same x, the same position and orientation of the end effector. And we are looking at what is that corresponding q. that will, of course, minimize the error between the n effector, the location, n effector location that is being specified against the forward kinematics computation. So we try to minimize that error. When that error is zero, that means that the n effector has already reached the location, the world location that was specified. And of course, plus the delta Q, where in this case, we try to minimize the delta Q or the configuration of the robot according to some criteria that you specify. It could be obstacle avoidance, it could be a minimization of energy during motion, it could be other things. And this function is an additional function because the robot is redundant. That means that there are many configurations. There's an infinite number of configurations or infinite number of postures of the arm that will bring about exactly the same world, space, position, and orientation of the hand. And so because of that multiple solution, we'll try to find the optimal solution. And so the optimal solution, Q star, is the one that brings about the minimization of this summation function. Okay, as a review, we say that in the last class, in our lecture 4, we have we already discussed the position vector and the rotation matrix. Position vector in this case, we have two frames. One is frame 1, the black frame, and the other one is frame 2, the red frame. And so when we mention about position vector, it is normally the origin of the reference frame with respect to the origin of another reference frame. So in this case here, 1P2 is the position of the origin of frame 2 with respect to frame 1. Okay, that's and this is expressed in this vector. And then there are 3 components, P1, P2, and P3. That's a vector of 3 components. Okay, and when we talk about rotation matrix, of course, the minimum number is 4, which is a quaternion. But in our case, we didn't discuss about quaternion. I prefer to discuss about the rotation matrix. In this class, I prefer to discuss about rotation matrix. And so this rotation matrix, we already mentioned that you have the X, Y, and Z or Z axis of frame 2 expressed with respect to the X, Y, and Z or Z of the reference frame or frame 1. And so X frame or X axis in frame 2 is expressed with respect to X, Y, and Z of the frame 1. So each of these axes, X axis, Y axis, and Z axis of frame 2 is expressed with respect to X axis, Y axis, and Z axis of frame 3. That's how we treat rotation, the rotation of frame 2 with respect to frame 1. Okay. So now to completely describe the relationship between 2 reference frames, frame 2 with respect to frame 1, we have a position vector 1P2 and the rotation matrix 1R2. Okay, so this is what we always want to know when we are given 2 reference frames. So we discussed about the homogeneous transformation matrix, that given that position and orientation, position P vector and orientation R matrix, we can combine them into a homogeneous transformation matrix A, excuse me, which is in this case 1A2 is the transformation matrix that describes the position and orientation of frame 2 with respect to frame 1, and is composed of the 3x3 rotation matrix and the 3x1 position vector. And so now this is a 4x4 matrix. Okay, and the inverse of that is this expressed in this form. Okay, and also last meeting we discussed about DH parameters. So DH parameters or the DH convention that defines the DH parameters uh, is a way of uh, defining the relationship between two adjacent reference frames in a robotic arm or in a chain manipulator. Okay, so in that, just for a review, we say that joint I normally rotates about the Z or ZI minus 1 axis. Okay, that's the convention. And XI is common normal between ZI and ZI minus 1, that one we know about, and Y completes the right-hand coordinate frame. And so when we are, this is a way of defining where are we going to attach the frames of reference for each of the link. So one link will have, for a chain manipulator, one link will have one reference frame attached to it. And that reference frame attached to it moves together with the link of the robot. So when those reference frames are already being assigned, then we can use the DH parameters. We can define now the DH parameters that will help us solve for the transformation matrix. So in this DH parameters description, I modified it so that students can, and me, myself, it helped me a lot many times. I can remember exactly how to derive the values of each of these DH parameters. So for when we're talking about the angles, which is theta and alpha, it will always be about. So about for theta, it will be about Z axis. And for alpha, it is about X axis. And for the distances D and A, for distance D, it will be along Z axis. And the distance A will be along the X axis. Okay? Okay, and then of course we know that the DH convention is dependent upon direction. So there should always be from and to. So theta will be about the Z axis from xi minus 1 to xi. Okay, so there is that sense of direction. So that one we discussed already, and the same thing for the rest of them. Okay, I prefer to be again in this case here about, and then from some axis to another axis, and then for the distances here, because these are rotations, we're just talking about axis here. For the distances, we're talking about origins. So along zi minus 1 from the origin of I minus 1 frame to intersection of zi minus 1 and xi, something like that. And when you're talking about AI, when you have along xi, again from the intersection, which is this is point of intersection, from that intersection to the origin of the ith frame. Okay, so that's already discussed from last meeting. I was just reviewing so that we can be refreshed of how the DH parameters are being derived. So once we derive the DH parameters, then the relationship or the transformation matrix can be defined, which defines the relationship between two adjacent reference frames. So the general definition for two adjacent reference frames, reference frame I minus 1 with, and frame I, that means frame I with respect to frame I minus 1, the transformation matrix can be the sequence of transformations from the distance of Z along Z axis along distance of D, then around about Z axis by angle theta multiplied by the distance transformation matrix corresponding to the distance along X by the amount A, by a value of AI, and lastly, transformation matrix of a rotation about the x-axis by a value of alpha. So in this case, this is alpha I. So given those all post-multiplication of matrices of basic rotation and translation matrices, we can derive the complete transformation matrix that defines frame I, the relationship of frame I with respect to frame I minus 1, based on the DH convention. So this is the transformation matrix that we are looking at all the time. Okay, so as you remember, we have an exercise in the class about a planar robot, 2 degrees of freedom, 3 degrees of freedom planar robot. We never use any DH parameters. We just geometrically solve the forward kinematics and the inverse kinematics problem. But in the full space, that will be quite troublesome if you just compute geometrically. So now we use the DH parameters in order to have a more general way of defining the end effector of the robot, the hand of the robot, the position and orientation of the hand of the robot, with respect to the base frame of the robot for any general purpose manipulator that can move in the full space or in the world space. And so this is the transformation matrix that defines the transformation from one reference frame with respect to the other. Okay? And so, for example, when we are doing the forward kinematics of a manipulator, in this case, this example, it has 3 rotary joints. And in this case, it's a planar robot. Again, still a planar robot, but with more joints, it can be, I think this is the Puma or similar to a Puma. But if you add more joints, then the geometric solution won't be enough. So we need to define how to attach the reference frames and define the Dinabet-Hattenberg parameters and compute the transformation matrices. And so if you compute, let's assume that in this discussion, this is a full spatial robot. And so we define the Dinabet-Hattenberg parameters. And so we're able to define the transformation matrices between 2 adjacent reference frames, from frame 0 to frame 1, from frame 1 to frame 2, from frame 2 to frame 3. And so to express the end effector frame, which is in frame 3, this is end effector frame in frame 3, we, with respect to the 0th frame, which is the base frame, in that case, this is the base frame, then we post multiply all these transformation matrices. Okay, and we note that this is the forward kinematics that we are talking about, where in this case, these are functions. The transformation matrix is a function of the joint values. So the Q, all these transformation matrices A can be solved when you are given the current value of the variable Q, which can change at a given time. And so with this post multiplication, we can find the orientation and position of the robot end effector frame at any given time as the Q changes. So this expression here is similar to this. The only difference is that here we specify that Q are the input, the values of Q are the inputs, while the position and orientation is the output. Okay, so in this case, this is position and orientation as well, the rotation matrix and the position vector, but it is computed based on the post multiplication of all the transformation matrices where Q is an input. Okay, and so we know that this is nonlinear. But luckily, when we express the velocities of the joint space of the joints, as well as the velocities of the end effector, position and orientation, then it linearizes the parameters. So in this case, we linearize the delta x dot is equal to j q dot, where j is called a Jacobian, and it linearizes the relationship between the joint space velocity against the operational space velocity or the world space velocity. So it could be treated as the incremental movement or the incremental change of Q multiplied by the Jacobian matrix J of Q will result into an incremental movement of the hand position and orientation. Okay, that's another way of expressing the linearity between the joint space and the world space. Now, let's go to inverse kinematics. As we mentioned, we use X. We use X as our allocation in the workspace or a desired location in the workspace, and then we solve for a Q that will give us that X. What are the joint values for each of the robot joints, so that we can have our hand in the world where this is X. And so again, this is the forward kinematics linearity equation. And if we solve for the inverse kinematics linearity equation, so we just take the inverse of Q on the other side, assuming that J of Q is square. So we can take the inverse. If it's not square, we can take the pseudo inverse. And we have now the delta Q. So the incremental movement of delta Q computed multiplied by the inverse of the Jacobian matrix will give us now the incremental motion of the joints. So this is very important, because now we know that if we need to move the hand by just the incremental movement, if we know what is the Jacobian, then we'll know exactly what is the incremental movement of the joints that we need to push the joints, so that we can have that exact incremental motion in the world space. Okay. So what is the composition then of this Jacobian matrix? Jacobian matrix is based on the first equation that we had in terms of velocities. So it is the partial of the position, the change in the position and position and orientation of the hand with respect to the change in the position and with respect to the change in the joint values. So if we take the x as x1 to have x1 and xm components, okay, then of course x is composed of a position vector and a rotation matrix based on our previous discussion. But to create a generality of how the partial differentiation is created, we are going to put the components of x as x1 up to xm, and the components of q as q1 as up to qn. So that means that there are n joints in the robot, but then there are m degrees of freedom of the world where the robot is moving. Okay, so if that is the case, now we can take each of the components. So partial of x is a vector, and partial of q is also a vector. So in this case, in this discussion, is a vector. So it has components x1 to xm. And so if you take the partial of the vector with respect to another vector, it will be a matrix in this form. And component by component, so partial of x with respect to partial of x1 with respect to q1, partial of x1 with respect to q2, up to partial of x1 with respect to qn. So we do that for every component. So partial of xm with respect to q1, partial of x, again, that xm with respect to q2 up to qn. And so it becomes an m by n matrix, the Jacobian matrix. So the Jacobian matrix then is our key to solving the inverse kinematics problem. We have seen this with the planar robot that we discussed in class. So how do we do the Jacobian then? How do we compute the Jacobian based on what we know? First of all, we will try to see what is the Jacobian composition, and we will look at the transformation matrix. This is the transformation matrix, the general transformation matrix that we have. And we see that for a Jacobian, it is a matrix of n by n dimension. Excuse me. We can subdivide it into columns, say column 1, 2, up to column n, depending on the number of joints. So that means each of these columns are vectors. So what is the composition of that vector? So this is the composition of this vector. It is a geometric, we compute it using geometric interpretation. We can analytically solve for Jacobian if you are given the vector of x, and we can compute it like this. Okay, but for a given robot, our limitation is that our x is composed of for the most part, we treat it as a vector, position vector, and a rotation matrix. So getting the partial can be partial of each of those components can be quite tedious or difficult to get. So we prefer to use the geometric Jacobian computation. So how do we, it will be much easier to compute the Jacobian this way. So how do we do that? So first of all, there are two major components. One component is the position vector, okay? And the other component is the z-axis or the z-axis. The z-axis, in this case, the zi minus 1 axis, as shown in the figure, is where the link I rotates. Okay, this is link I. This is link I, and this link I connects up to the n effector. As the link I rotates, in this case, only link I rotates. The rest of them are locked in position. The rest of the joints are locked in position, and so we are looking at what could be the resulting motion of the n effector if joint I rotates about the zi minus 1 axis. Okay, so you cross product of this axis against that position vector, I minus 1 pn. Okay, this is the position vector, and then we get the rotation of this axis cross with that position vector to find what is the n effector position and orientation for this particular joint motion. Okay, so that's how we do it. And so what about the rotation here for 0 Ri minus 1? It's because we need to express this P1 I minus 1 Pn. It should be expressed with respect to the base frame. And so it is just this vector is expressed from I minus 1 to n, okay? But then it's expressed based on this reference frame. In order to change the reference frame, the expression from frame I minus 1 to frame 0, we multiply it with a rotation matrix. Okay, so now this position vector is expressed with respect to the base frame. And the same thing as the z-axis, the zi minus 1 or zi minus 1 axis is expressed with respect to the base frame. So all of these two components are expressed with respect to the base frame. So we're looking at a revolute joint. In this case, that's a revolute joint that is driven by motors, electric motors. So this is the position part. And then for the orientation part, you just take the value of the z-axis, okay, of the zi minus 1 axis. So where can we get all of these values? We can get all these values from the transformation matrix, okay? So where in the transformation matrix? This is our transformation matrix, okay? But before we do that, okay. We can get this from the transformation matrix. So if this is your transformation matrix, let me do the annotation. It doesn't come out. Okay. Yeah. Annotate. Annotate. Okay. So annotated. So we draw. So this is your transformation matrix. Okay. From okay. So you have how do you compute this? Okay. So this P, the P part, okay, is this part. Okay, you're going to compute it from there. And of course, the rotation part will be this 3 by 3. Oh, sorry. Undo, undo, undo. Okay. The P part is this. That's the 3 components. That's the one. And then the rotation part will be this one. Okay. So that means that, and then the Z part, the Z part is called an NOA. I thought I already put this one here, but the Z part will be just this. Excuse me. Because this is the X column, the Y column and the Z column. Is that clear? I want to make it much clearer. That is the Z part. Okay. So now, how do we do this then? So we need to compute A. Okay, let me just do this very quickly. So you need to have 0, A2, for example, or A3, okay, is equal to, you have 0, A1, 1, 1, 1, A2, 2, A3. Okay, and maybe it is, I'm looking at what is your third, okay, third joint. We're looking at I is equal to 3. I is equal to 3, for example. And so if I is equal to 3, now you have, this is the 0, okay, I is equal to 3, and probably you have your, let's say, for example, your N, I is equal to 3. I cannot change it. So here, you say N is equal to 6, for example. If you have N is equal to 6 and I is equal to 3. Okay, so how to solve this? And so you need to have the 0, if I is equal to 3, so 0 is Z2. Okay, so you need to have a 0 Z2. You compute 0 A2. 0 A2. Okay, 0 A2. Okay, from there, you can compute your 0 Z2. Okay, now you're done with that part. Then what about the 0 R2? Yeah, you can also do that because as we mentioned, the R is this part. Is the spotlight. The R is the R is this part, and this is the Z part. We can take 0 A2, for example, the Z part, and the R is the whole thing. And so now you can use. So here, from here, you can also use 0 R2. Okay, so that takes care of that. So this and that are taken care of. What about this one? So you need this 2PN. Okay, so that means that you need to compute 2AN. Okay, 2A6, for example, because you have 6 joints, and so you have 2 from there. Once you compute that, then you can have 2P6. Okay, then you can compute this, and so that means that in that case, this is already computed from here, and this is already computed from there, and this is already computed from there. Okay, and your, for the orientation, it is already computed there. Okay, so you have to do this recursively in order to get all the elements of the column for a revolute joint, for example, for a column that is corresponding to, in this case, column 3. Okay, so these are the elements of your column 3, and you just do accordingly. You cross the top part, and the other part you just fill in the information. Okay, so you continue you start from 1 up to n, then you can populate the columns of the Jacobian matrix. Okay, I hope that's clear. And so we stop, clear all drawings, we stop annotating. Let's continue. So now, I've seen the example for the third joint for a 6-link robot. So now, for example, in this case here, you have to continue. As I have shown you in that example, in this case, because this is with respect to the base frame, It's a lot easier. You don't need to multiply because 0R0 is an identity matrix. So now you have this part when you are considering join 2 up to now the join 5. So this is how you're going to compose the Jacobian matrix column by column. So now if we do the workspace control, okay, so we know that from our previous discussion, we need to have a position error for the planar robot. So the position error for the planar robot, you're going to uh, change to see the error between a desired position, which is PD, the desired position that's specified by the user, and the actual position that is based on the feedback from the robot. Okay, this actual position can be computed from the forward kinematics. Okay, so we do this, and then this is the P. The P is computed, of course, from the forward. P is equal to F of Q, okay, which is part of the X, okay. So that's the feedback, and then now you compute your error P, position error. And for orientation, it's a little bit complicated. So here you have NOA. So NOA is the same as the X, Y, and Z axis for the rotation matrix. This is what we, in some authors, they prefer to say normal. I think, I'm not sure about O. Normal is normal. Normal, I mean, perpendicular, of course. And then A is approach. A, I forgot what was O. But then this is just another way of saying X, Y, and Z axis. Okay, like that, which we have discussed before. Okay, so now you have a desired X, Y, Z for that is set by the user, and then you can have the actual R, which is done by forward kinematics. So again, by forward kinematics, you can compute the transformation matrix, and then you can get the R. Okay, that is this is by forward kinematics using the okay. Of course, this is rotation matrix computed from like that, but to compute that, it will be, for example, 0A6, for example. If there are 6 joints, then you have 0A1, blah, 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 up to 5A6. And then you take from there, you take the rotation matrix. Okay, that's how you get it. But then the question is, how do you define your desired rotation matrix? Well, you can define it. There are ways to, for example, if there's no rotation, then the rotation matrix, if the desired rotation is the same as the reference frame, there's no rotation, and so the rotation matrix is an identity. So, but if you want to have a certain rotation to a certain axis, then you can define, you can either follow the convention of roll pitch convention that people are using. But for me, I mean, because people are using that, you can use that. But nobody is stopping you from computing R based on, for example, you compute R based on the rotation from x-axis by alpha, for example. Okay, and then multiplied by R with rotation matrix and Y based on beta, like that, and rotation about Z based on gamma. Okay, so if you have 3 rotations, you can always do that, and then you can specify your desired rotation here. Or you, as I mentioned, you can use roll pitch and yaw convention that is popularly used by many people in the industry. Okay, so that's just one that is a little bit complicated, but it is good to note that of all these computations, okay, then this will result into a 3x3 vector, and the same thing as this one. This one will result into a 3x3 vector as well, because here, of course, component-wise, you can compute that this 3x1 vector minus 3x1 vector. The result is a 3x1 vector. Now here, this is a 3x1 vector because it is from this one, this 3x1, this 3x1, and 3x1. cross with 3 by 1. So the result or 3 by 1 vector is a vector plus a 3 by 1 vector plus a 3 by 1 vector. So the result is a vector. So now when you try to compute the error in terms of position and orientation, now you have two 3 by 1 vectors. Now you have a 6 by 1 vector that expresses the position and orientation errors. So now in terms of doing proportional control, so you can have this, the error multiplied by a proportional gain, that is your controller, U. Now you can multiply it with the inverse of Jacobian matrix, okay, to be able to compute the corresponding delta Q, or the motion in the joints that you wanted, okay, the incremental motion of the joint that you wanted from the given information of the current Q, where in this case you have a current Q here. This is the current Q. Okay, so now from this current Q, you also have the current position and orientation here from this error term. Okay, then you compute that. Now it will give you the new desired. It will give you the step that you need to do from the current position, from the current the joint step that you need to do from the current joint values that you are given. Okay, so now that completes our control equation. So let's continue. So just to wrap up the information that we have discussed here. So in terms of control implementation, it is just exactly as the two-link planar robot that we did. The only difference is that now we express position and orientation, the Jacobian matrix, the transformation matrices in the full space, okay? So for example, you're given a planar robot, so you're not given a planar robot, you're given a full space robot, fully spatial robot, excuse me, and then you assign random variables of theta 1 up to theta n for the joints. And then you compute the Jacobian based on the geometric Jacobian that you mentioned. Of course, we need to identify your transformation matrix. And so you need your, you need to identify your Denavet-Hartenberg convention, DH parameters. Okay, so you need your DH parameters. So you need the transformation matrix from 0, A, N, okay, 0, A6, for example, okay? And then once you know the relationship, once you know the DH parameters for all joints, then you can compute your transformation matrices for two adjacent joints. Now you can compute for your A0, 0, A6, for your 0, A6, and then that is for the forward kinematics, and then you compute for your Jacobian matrix. So when you compute for your Jacobian matrix, you need to know you need to compose the columns of the Jacobian matrix. The columns of the Jacobian matrix will be composed using the geometric Jacobian that we just discussed a while back. And so using the information of these transformation matrices components in terms of P, in terms of Z or Z axis, and in terms of R. Okay, then you're done. Okay, you know your Jacobian. So once you know your Jacobian, then you compute your Jacobian, and then you will get your where your X and Y are from the forward kinematics, X, Y, and Q are the current joint values that is given. And then you now set your desired value of X and Y. Now it's X, Y, and Z position, and then orientation you can set the same way as we discussed in the previous slide. And now once you compute then you will know what is the incremental value of the delta Q by, of course, implementing this control equation. Okay, then you step and then you update your step incrementally. Okay, now this part here is of course actual position and orientation, and then this is the desired position and orientation, which we discussed already previously. So the error in the position and orientation multiplied by the KP gain times the inverse of the Jacobian, which we compute from the from here, from the relationship of the transformation matrices. Okay, then you will be able to update your Q until you reach your final destination, where the error part will become minimal, and so you reach now the desired X that you specify. Then that's it. Okay, so again, we're not talking about redundant robots here. We're assuming that the robot, the Jacobian J, is square. That means that the number of joints is equivalent to the number of degrees of freedom of the joints is equivalent to the number of degrees of freedom of the workspace. That means that, for example, for a two-link robot, it is specified to move in a plane, and for for a 3D joint, three-dimensional joint in the world, where it's specified to move in a 3D world, then you have 3 joints. And then for full spatial, you have 3 position, 3 degrees of freedom of position, and 3 degrees of freedom for orientation. Then you have 6 degrees of freedom robot, is equivalent to Puma arm, and then other 6 degrees of freedom robots are available now. And later part, we can discuss redundant robot, where we're going to specify the posture and how we are going to do extra things aside from the finite number of postures that the robot can have if the robot is not redundant. But then with the redundancy, even with 1 degree of redundancy, that means 1 joint, extra joint in the robot, you can have infinite number of configurations that the robot can do to do other things. For example, avoid obstacles and do many optimization work. Okay, so that's it for today, and thank you for listening. Bye. Now,